Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and take a look at our problem this morning for the optimization strategy, right, when we use calculus to determine the optimal solution for a given problem in context. And to help us with that, we can refer to our single-page, one-sided optimization strategy handout. Make sure that you have that at the ready because I'll be calling on you to share steps along the way, and we can use this kind of as a starting point for our discussion today. We'll continue our optimization practice. Then we're going to take a look at some more graphical applications of the FTC Part 2, and then you'll get a chance to work and practice. We've got a single stamp day as you practice with the FTC Part 2. Okay, so after reading the problem, right, we want to write down our goal. That is what we're trying to do, what we're trying to optimize. Maybe we're trying to minimize cost. Maybe we're trying to maximize profit. Let's see in this case. Horatio must construct a rectangular pen that encloses an area of 216 square meters that has a middle partition to separate the milking cows from the dry cows. What's the minimum length of fence required? After reading the problem carefully, right, what is our goal? What is it that we're trying to optimize here? Hayden?
We're trying to minimize the length of fence required.
Absolutely. We're trying to minimize the length of fence required. So we're going to go ahead and write that down. Our goal is to minimize the length of fence required. This will provide the direction and focus for the rest of the problem. If we're trying to minimize length, we'll end up writing a length formula for the fencing to be used. Then we're going to go ahead and rewrite that as a length function of a single variable, right, that will end up performing either the closed interval method or the first derivative test or both, or the second derivative test, all with the goal of answering our original goal statement. Okay, so what does step 2 then ask us to do? So what's step 2 from our strategy ask us to do? Grace?
Draw a picture and label relevant quantities and variables.
Awesome. So I did my best to provide a picture for you, and check out that clip art. Gotta love clip art. So let's label this picture then with relevant quantities. So we can tackle this a couple different ways. I saw several people were using sort of my picture here to use an unknown horizontal distance. We've got to label this unknown horizontal distance as x. And then I saw some people labeling this unknown vertical distance as y. And that would be a good idea so that we kind of keep used to our horizontal and our vertical. All right, so let's go ahead and go to step 3 then. So for step 3, what does the strategy ask us to do? Joel?
Write a formula for the quantity you want to optimize.
Great, so we've got our goal, minimize length. We want to minimize length, so we're going to write a length formula, L equals, right, for our formula. So let's go ahead and take a look at our picture. Based on our picture and our variables drawn, what formula would give the length L of the fence? I'll go ahead and start it. L equals there. I'll go ahead and start it. So let's go ahead and fill it in based on our picture here. What would that be given by? Marissa?
2x plus 3y.
So 2x, that's the 2 long horizontal distances, top and bottom, and then 3 vertical partitions, so plus 3y. Awesome. Raise your hand if you get a similar formula, right, depending upon your labeling. Way to go, you guys. Thanks. What's step 4 then? James?
Use relationships in the column and or given information to write the quantities formula as a function of one variable. Consider its domain.
My favorite step. Thank you. We're going to use relationships in the problem, like given information, etc., in order to rewrite this formula that now currently length depends on 2 different variables, x and y, as a function of one variable, just L of x or L of y. It doesn't matter. Sometimes it's easier to rewrite it with a single variable, either x's or y's. In this case, we've been comfortable working with x's and we just know one day, so maybe we'll aim for rewriting this as a formula L of x. Okay, what information haven't we used then in our problem? Michael?
The 216 units squared.
Yeah, the 216 meters squared is the area that must be enclosed. And so we can go ahead and use that information to write a constraint equation, solve that constraint equation for y, and then substitute in for this y here so that I just have x's remaining in my L function. So let's go ahead and do that. My constraint is that my area of the pen equals 216 square meters. And my area based on this picture would be what in terms of x and y? Riley Freeman?
X times y.
X times y. And so it looks to me like my area of that pen, x times y is 216. Therefore, if I were to solve this for y, in terms of x, I could plug into my L formula and have a function L of x with a single variable, just x's. So I'm going to go ahead and rewrite this y equals, looks like 216 divided by x. So 216 divided by x. And now I can write my L of x formula. So L of x will be given by 2x plus 3, and then I'll substitute in. So I'm going to substitute in now. My expression for y is 216 over x. Awesome. Okay, ladies and gentlemen, so who is able to generate a function, L of x, with a single variable? Who got all the way to a single variable? Yes? All right, let's go ahead and copy that and bring us to our next page then. Thank you. We'll consider its domain to complete James's step. So we'll go ahead and grab this. And we'll consider its domain. So it appears to me that x stands for the horizontal dimension, right, of the pen that we're going to make. In this case, my function L of x has an x in the denominator of a fraction. Therefore, my closed interval method, where we've considered 0 as our leftmost boundary value for x, depending upon what the problem looks like, is not going to be admissible. And so we can't, right, do a closed interval method on either side. It looks to me like we're not going to be able to do our closed interval method, but that's okay, because we can still perform our analysis using the first derivative test and still answer a question that was asked, and that is right, a minimum question, a minimized length of fence. So let's go ahead and do a quick rewrite, and then let's get to our first derivative test. So I've got L of x, so much better. So then 648, is that right? 648 over x? Yeah? Awesome. Okay, let's get to it. So my first derivative then of L will tell me all about increasing versus decreasing behavior. So we want L prime. And it looks to me like if L is 2x plus 648 over x, then that L is going to differentiate to the derivative of 2x is 2. And then remember, this is a constant times, right? That power function 1 over x, the reciprocal function, which differentiates to negative 1 over x squared. Remember, the current exponent negative 1 times the base x to the 1 less is to the negative 2. So my final answer would be negative 1 over x squared times the constant out front. So I'm getting negative 648 over x squared. Raise your hand if you had this first derivative L prime. Okay, good. If you didn't, let's go ahead and get it down now, and we'll go ahead and perform our sign diagram chart. On my sign diagram chart, I'll put any critical values. Call it critical values, are a result of L prime equaling 0 or being undefined. And so oftentimes it's helpful, right, to rewrite this as a single fraction. What I'll do is I'll go ahead and multiply this this 2 by x squared over x squared to create a common denominator, just so that I can rewrite. That's kind of a good habit to get into as we go and generate our critical values. And so I'll make this 2x squared minus 648 all over x squared. And critical values can come from two places. They can come from L prime of x equaling 0, which would be the top. Will that ever equal 0? Or from L prime being undefined, if I have a fractional expression, that would come from the bottom, equaling 0. All right, so are there any critical values? Yeah, it looks to me like that top 2x squared minus 648 equals 0. That's going to happen when x squared equals, go gadget arm, 324, is that right? 324? And I believe that's a perfect square. That means x is given by the positive and negative square root of 324. And we're going to purposely just take the positive one because we're dealing with a dimension of fencing, so we're not going to have a negative length. And so what is my critical value that is the result of L prime equaling 0? Tyler? 18. Awesome. So it looks like we've got a critical value at x equals 18. Are there any values of x for which L prime is undefined? Yes. if the bottom of this fraction equals 0, then L prime is undefined, and that happens when x equals 0. So I've got critical values at x equals 18 and x equals 0 after considering my L prime equaling 0 or being undefined. What questions do you have up to this stage? And we're all ready for our y prime number line. Just like our first derivative test back when we were doing increasing versus decreasing behavior of graphs, now we're doing increasing versus decreasing behavior of functions in context. So let's go ahead and make my y prime number line, but I'll label it L prime, right, our L prime number line. On it, we'll go ahead and include any critical values that are in my domain. Because we weren't able to include 0, right, in my domain, it looks like we don't have to include it on here. It would be kind of a stopping point, right? 0 would kind of be a stopping point of this L prime number line. I'm just going to put then 18 here for my only critical value of x, which is on my domain, and perform a signs diagram test. So here we go. Convenient x value to the left of 18. As I consider my L prime expression, I'll go ahead and choose 1. 1 is to the left of 18, but still within our domain of permissible values. So I'll go ahead and put 1 into L prime, and I can go into any form. I'm going to go ahead and put in this form because I see 2 minus 648 over 1 is 2 minus 648 is very negative. So it looks like L prime is negative on the interval to the left of critical value x equals 18. A convenient x value to the right of 18. I want to choose something that I can still evaluate okay. If I pick 20, then that would be 400, and 648 over 400 would be 6.48 over 4, which would be about 1.5. 2 minus about 1.5 is still positive. Remember, I don't need an exact value, I just need a sign when I'm performing my signs analysis. So it looks like L prime is positive to the right of x equals 18. All right, what has this told me? Well, in the absence of a closed interval, right, I was unable to determine a domain with endpoints in this case. Now I know that my function L is increasing, that is the length, is decreasing, the length of fencing needed is decreasing up until x equals 18, right, meters, and then increasing thereafter. And if I'm trying to minimize my length L, then this indicates a local minimum, right, for the problem. Since there's no other critical values, there's no other places where we could change direction, so it's also going to be an absolute minimum using that line of reasoning. We weren't able to perform the closed interval method, and yet we're still able to answer the questions asked using our first derivative test. All right, so let's go ahead and see what that is then. Because the question still asks, what is the minimum length of fencing required? We'll go ahead and still make an L of x chart, and on that chart, we have to include 18. Now, this is not a closed interval, but if we wanted to, we could include, right, other values on here, just one on either side in order to make sure, right? And so we could include other values on here in order to make sure. In order to do that, I could pick something that is convenient, right? We could pick 1 would be easy to evaluate, and we could also choose something that would reduce with this 216, so maybe 108, right? Now, these values are optional. I only chose them to verify that this was in fact a minimum in comparison with nearby values. So let's go ahead and consider the value of L when x equals 1. When x equals 1, L is given by 2 plus 648 over 1. So 2 plus 648 is 1,296. Is that right? 1,296 meters? No, 2 plus 648. It's just 2 plus 648, no 2 times. So 2 plus 648 is 650? Is that better? Oh, gosh. We're gonna need a bigger boat. We're gonna need more fence. 18, okay, let's go ahead and do 18. And so 2 times 18, right, would be 36. And then 648 divided by 18 would be what? 36? Again, is that right? So 36 plus 36 is 72 meters, is that right? Bless you. And 108, why did I choose 108? Oh, because I was looking at the top definition. And so 108 is half of that, so that's 2, so that's 6. So 6 plus 216 is 222. Looks like 72, right, meters of fencing is a lot less than the surrounding fence values that I chose, one on either side of my critical value, x equals 18. So the moral of the story is what? The minimum amount of fencing required would be 72 meters in order to construct such a fence. And so minimum amount of fencing required is 72 meters. Raise your hand if you already found 72. Did anybody else already find 72 before we begin the discussion? That's great news. And now we've only done, right, we've only done a couple optimization problems, and today our focus will be continuing to work with optimization. And then we're going to look at a graphical application of the fundamental theorem of calculus part 2 again, right? See it again for the third time, and I think it'll really click for you. A chance to earn a stamp with a partner, not cooperative learning groups, or just partner today, and then a chance to work on your assignment. All right, so let's go ahead and take a look at our schedule. Because of where spring break fell, some of you will like the schedule, some of you won't like the schedule. I think that it's good and bad. So today we're practicing with more optimization in a graphical application FTC part 2. Next class we'll have some structured review time. We're going to take a look at a couple of hodgepodge things that are included in the AP curriculum that don't really fit into necessarily any of our units in a great place. The change of limits is one of the few items where we need to use substitution. I talked about at the beginning of the year how if you were able to know your derivative rules very well, you wouldn't need to use substitution on those unit tests. Now we're to the time where we need that use substitution in order to investigate change of limits. Derivatives of inverse functions is something we'll look at briefly together, and then you'll have the rest of the time to review. Prior to your spring break, there will not be a Moodle post this week or over spring break. Okay, so there's no Moodle post this week or over spring break. And then we'll have completed the bulk of our material for the AP curriculum, other than particle motion. And one more look at position, velocity, and acceleration, which is always a big thing. That'll be our final unit, Unit 10, before some practice. All right, which means when you come back from spring break, you'll be taking your Unit 8 test. Okay, you'll get your concept and skill guide then over 2 weeks in advance to work and prepare. Now, you can decide how you'd like to chunk up the time. And so you could review a little bit over spring break, or you could wait, right? Depending upon how you want to do it, you will get time in here, but you're going to have to figure out some way to make sure that you can perform well on that Unit 8 test. You're going to have all this stuff well in advance so you can decide what works best for you in terms of your individual preparation. All right, questions about our schedule? All right, then let's go ahead and pause the recording and we'll take care of our homework check. Thank you, ladies and gentlemen. So let's go ahead and take a look at a couple more optimization problems together to practice with our strategy. Thanks for having that handout ready. So let's take a look now at the separate handout we received on day 3 last class. The open top box problem is kind of a classic, right? Classic problem situation. We're going to start with a standard piece of typing paper, 8.5 by 11 inches. We're going to cut out squares, right, from each of the 4 corners, and then fold up the remaining tabs so that we create a rectangular solid without a top, an open top box. And so such is the name for this problem. Everybody, let's go ahead and find that and find the maximum, right, the maximum volume box that can be constructed in such a way. So we'll go ahead and take a look at my 8.5 by 11 inch sheet of paper. We'll write down our goal. Our goal is to maximize the volume of such an open top box, and that'll provide the focus for our problem. So we're going to maximize volume. Okay, ladies and gentlemen, let's go ahead and make a nice picture of this. So we'll go ahead and get our 8.5 by 11 sheet of paper. And we know that we're going to cut out squares of side length x from each of the corners. And it would be pretty sweet if we made that red. And it'd be pretty sweet if I just grabbed extra ones of them. Yeah. if we were to construct, right, an open top box by removing these corners, each of side length X, right, for my 8.5 by 11-inch sheet of paper, can you visualize the tabs that would remain to fold it up? Nice pick. And so let's go ahead and label some things. I'll go ahead and label the dimensions of my square there, right, are X inches. We know the entire piece of paper was 8.5 inches wide. And 11 inches was the entire piece of paper. Great. Okay, so after drawing our picture and labeling with relevant quantities, we're all set for our volume formula. So if we consider this problem, what would our volume formula V equals B? Well, it looks to me like we have a rectangular solid, and so the rectangular solid's volume is given by length times width times height. Yes, so in general, my V formula for a rectangular solid box will be given by length L times width W times height H. The challenge will be step 4, using information in that problem, right, in the physical constraints, to rewrite this volume formula as a volume function. Now, many of you have seen a problem similar to this in the past. How can we get our x's involved here to rewrite this as a volume function v of x, right? Well, let's go ahead and take a look at the length here. The length of this box, we'll call it L. The length of this box, L, started at 11, but now we've cut out a square on top and a square on bottom, which would leave me with how much inches? How much inches? How many inches? Well, start with 11 and then take off each of those corners. So I have L equals what? 11 minus 2x. So 11 minus 2x is going to be the length. In the same way, my width W started out at 8.5 inches, and then we took off 2 of the squares, so we'd be left with 8.5 minus 2x. And then lastly, the height H. What? What's the height H of the box going to be? Yeah, it's going to be X inches tall, because we fold up those flaps and we'd be left with X inches tall. So I'm going to go ahead and put my little fold dashes. I always need that in my little schematic if I'm going to make all the directions. I like my little fold lines on there. There we go. There, now I can see that when I fold up those flaps, the box will be X inches tall. That's pretty sweet. Awesome. So let's go ahead and rewrite this and then consider its domain. So we'll go ahead and rewrite this. It looks like v of x is given by, and we'll do some multiplying here. So 888, half of that, half of 11.55, 88, 92.5. So I'm getting 93.5 minus 22x minus 17x minus 39x. You guys catch me when I make a mistake here. I'm never good with numbers. Plus 4x squared. Multiply the x through, shown on the back side, and v of x is given by 4x cubed minus 39x squared plus 93.5x. Did I do that right? All right, so if I made a mistake, I'm counting on you guys to catch it, and now we consider our domain. In this case, right, the minimum side length square, if I didn't cut out any dimension squares and had a flat piece of paper, it wouldn't hold, right? That box wouldn't hold much. But if we wanted to consider the domain here to aid in our final evaluation and make sure, we could say 0 would be my minimum side length x up until, and I'm cutting until when? When do I run out of paper? Riley?
At 4 1/4.
At 4 1/4 inches, we'd run out of paper right here. So that would be my maximum. We'd run out of paper down in here before we'd run out of paper up here. So 4.25 inches would be my maximum x value. And again, that would result in a width of 0. And so these are my extremes, and I'll just throw those on. on my XYT chart, right, to compare those volumes with the hopefully maximum that we find in the middle of that critical values. All right, so let's go ahead and copy this over to the next page. I'm going to take this with me. All right, so let's go ahead and do our first derivative b prime. Go ahead and tell the class when I call on you. What would my expression for b prime be? Annika? Awesome, thank you. Now to get my critical values, I consider those values of x for which b prime is undefined or equals 0. Since I have a nice polynomial equation here, a quadratic equation, there's no values of x for which b prime is undefined, which means I need only consider those values of x that make b prime equal 0. Are there any values of x that make b prime equal 0? I don't know. We'll set equal to 0 and solve. Although I'm not thinking that factoring is going to be my way to solve that. That's okay, so we'll go ahead and audible. I know it's a Monday, but what a way to start out the week. No, we got to save that for Thursday when things get really tough. All right, so here we go. A, B, and C. It looks like we can simply use the quadratic formula where my value of A would be 12, negative 78, 93.5. And I know that my solutions then, X would be given by the opposite of B over twice the value of A, plus or minus the square root of B squared, it's always positive, minus 4 times A, yikes, times C, close radical, all over twice the value of A. I'm so used to my advanced algebra way of doing this, where we consider this as 2 separate parts. Then it takes a lot for me to do this. All right, I see no problem going to our graphing calculator home screen. Remember, we're using second calculate maximum or second calculate minimum to optimize. We're just going to our home screen to evaluate that to get our critical value. So I see no problem in doing that. Let's go ahead and go to our home screen. And on our home screen, I'm just clearing out, and I'm going to go ahead and enter 78 plus second radical. That's always positive, so I'm just going to do 78 squared minus 4 times A times C, close radical, close numerator. All over twice the value of A is 24. How do I do? Ooh. I got 4.915, right, if we keep our 3 decimal places. That's great, except it's not great, right? What's wrong with this value? Yeah, it's outside of my range of permissible x values. In fact, I would have run on a paper at 4 1/4 inches, and here this is 4.9 inches. So this is not an acceptable critical value. It's not going to lead me towards a solution to the problem. So what do?
Try the other.
Oh, right, we only did the plus or minus, and so we only did the plus, and so try the other one. And I wish I could figure out how to grab that. Can I grab that like this? Press enter? Should we try? Not as good as second entry, I guess. Hey, that was a pretty good guesser. Hey, that's a lot better. 1.585 is within my range of permissible x values, and so this looks like the way to go. And so it looks to me like we've got critical value at x equals 1.585 ... Now, I don't want to lose accuracy, right? We want to make sure that we're rounding our final answer, when appropriate, as a decimal to the nearest thousand. And so what I'm going to do to avoid compromising accuracy is to keep these decimals and store them in my calculator by using the store button, that first column, right? That first column right above on is the STO for store. I'm going to store this in alpha A. That way I can call it up for the duration of the problem without compromising accuracy. So STO, and then I'll do alpha A or whatever letter you want to store it as. I'm going to store alpha A because it's by the alpha key, and so it just saves time and easy for me to do it. That way, every time I enter alpha A, it'll pair that with 1.585. So I stored it, STO alpha A, enter, voila, and now I can take it with me whatever expression I go. All right, let's go ahead and make my closed interval then. So we were able to determine a closed interval, so we can do our closed interval method. I'm also going to do an A prime chart, right, just so I can verify. So I'm going to go ahead and do both. That way I'll be confident in my answer. So I'll do an A prime number line. What's that? I'm sorry, B prime the whole time. Here I just stored an alpha A, so I'm all excited about A. I'll make a B prime number line. Thank you, Hayden. And my critical value is just alpha A on here. So if I define that as A, then I can actually use an A on my chart. And I'm going to be plugging in values to the left of 1.585 into B prime. Thank you for labeling your thing. So I'm going to go ahead and plug 1. Right, if I plug 1 into B prime, then I would get 12 times 1 squared minus 78 times 1 plus 93.5. I don't need to do this, but I'm going to use alpha A in my subsequent ones. So let's see. 12 times 1 squared minus 78 times 1 plus 93.5 is positive or negative? It's positive. So we've got a positive values of V prime to the left of 1.585. And now let's choose a community value to the right of, like 2. Good job. Stop. When I get it. No. I don't know. We'll see. I got negative. Recall, if we have a closed interval, we don't have to do that A prime number line, but I'm going to do it because I want to be confident that I found the maximum value, and that increasing then decreasing behavior by V, as evidenced by my V prime number line, switching from positive to negative, makes me feel more confident in my answer. All right, so let's go ahead and do it. I want an X, V of X, T-chart. What am I going to put on there? 0, my left endpoint, A, my critical value, and 4.25, my right endpoint. Now I'll get my volume values from each of those and compare, and it looks like I'm expecting to see the maximum right here when X equals A, 1.585 inches. Let's see. So where can I go? Well, I'm going to actually do my volume formula. Again, I'm not graphing it. I'm just using this to evaluate. So we want 4x cubed. I think the math 3 shortcut's pretty sweet. Minus 39x squared. Uh-oh. Plus 93.5x. Huh? And we want to evaluate that at 0 and alpha A and 4.25. I don't need it. I can just write it down. 0, 66.148. And 0. So by golly, it looks like the maximum did occur at my critical value of about 1.585 inches. Hooray! And produce a volume of about 66.148 cubic inches. The problem is that the question didn't ask that, right? What did the question ask? What did our question ask? The dimensions, and so we have to go actually and look at my dimensions, length times width times height, to answer the question. So to me it looks like my x is the height, so we found that. That's A, which is 1.585. by, and then I'm just going to do 8.5 minus 2a, and I'm going to do 11 minus 2a, and then I'll tell me my dimensions. So to answer the question that was asked, I'm going to say 1.585 inches by, and on my calculator I'm simply going to do 8.5 minus 2a, there's another argument for storing, and 11 minus 2 alpha a. So it looks like 5.329. And lastly, 7.829 are the dimensions of the box that maximize volume. That was a pretty sweet problem. Dang. So in pre-calculus, that was fun. We just made the function. The key was the translating from the picture to get the 11 minus 2x and the 8.5 minus 2x times x, and then doing the graph so I can calculate, right, maximum. Here, we use calculus to find the critical values and determine that maximum analytically. So that's pretty sweet. Let's go ahead and take a look at the fish tank problem. So the fish tank problem is next. And here, it looks like you're going to build a fish tank, right? You're going to build a fish tank that satisfies given constraints, but is cheaper, right? So everybody take a minute and read that, and then I'm going to call on you to tell the class what our goal of this problem is. Go ahead and read our fish tank problem setup, and then I'll call on you to share with the class our goal, step one. What is it that we're trying to optimize? All right, so at the end of the day, when the dust has settled, right, what was our goal? What would I hope to have done here? What's our goal here? Kyle?
So get this with the least cost with 72 cubic feet.
Absolutely. So we want to maximize or minimize something. We want to minimize cost, and that'll be our impetus for the problem. So we want to minimize cost. Good, thank you, Kyle. So minimize cost, which means we'll be writing a C equals formula for cost, and then a C of X, or C of Y, or C of L, or whatever, in order to get my function on a single variable. Great, so let's go ahead and draw a picture. It looks to me like the width was always going to be 5. It's still like an open top box. Oh gosh. I like to make drawings, just I'm not very good at it. So I wish I could make better pictures, but I can't, so we're going to make this always 5. Yes? We're going to make variable depth. We're going to make our depth or width or length maybe, L. And variable height, H, maybe. All right, so based on my haphazardly drawn and fairly cruddy pictures, we now have to write a cost formula. So based on that picture, right, where am I going to be spending money? Well, I'm going to spend money on the base. I'm going to spend money on the sides, front and back, and then the 2 sides, but I won't need to include any material for the top. It'll be open top for this aquarium, right? It'll be open top. All right, so what is the cost of the base? The bottom. Well, my bottom is an area, so that is a rectangular pane. I'm sorry, I can't handle this, I don't think. I tried to for a while. I tried to handle it for a while, but then I couldn't handle it. There. That's much better. So my, I know. So the base, right, the base rectangle is gonna be 5, is that, what's the dimension on it, feet?
Yeah.
5 feet by L feet, right, for the area, and then times my cost. And what's my cost for the base? $10, right, per square foot. So it looks to me like I'm going to start out with my C formula, and I'm going to get C equals, so base is 5 times L times $10. That's a lot. Plus, I need it for the front and back. So the front is going to be width 5. Times height H. Times green cash money, how much do the sides cost? $5 per square foot, so times another 5. And then there's not only the front, but there's also the back. And so I need a times 2. Is that right? So 5 by H, right? Times $5 per square foot, times 2 of them. Did I get everything? Is it 5 for the sides?
Yeah.
Yeah? So it's $10 per square foot for the base pane, the bottom of the aquarium, but then the side panes are cheaper material. Is that right? Awesome. We'll want to go, I feel it, last term. So what's our last term here? Plus, we still need the long sides. So the long sides are L long times H high square feet times $5 times 2 of them. Times 2 of them. Did we get everything there? Did I miss anything? Oh gosh, this is crazy. I'm gonna make that a little bit cleaner because right now it's scaring me. So let's see. We've got our formula is C is 50L plus 50H. You guys catch me when I make a mistake. Plus 10LH. 10LH. This is cool. So, because we're working with lengths and heights here, and we're used to working with x's and stuff like that, and so let's see. How can we rewrite this formula in step 4 to be a function of one variable, right? Just h's or just l's? I give up. Oh, what haven't we used here? Right? What constraint haven't we used? The volume is set, isn't that fixed? And so my volume of this aquarium is going to be, Kyle, you told us at the beginning, was it 72? 72. So the volume is 72, and so I'll go ahead and use that constraint. My volume V, which would be given by a rectangular solid 5 times L times H, is fixed at 72 cubic feet. Therefore, I could solve this for L or for H, right? I could solve this for L or for H and then plug back in. Which one do you guys want to solve for? Looks like we've got 2 L's and 2 H's, so I don't know if it matters. What's that? Go with L and work with H's? Okay, let's solve for L, which then would be given by 72 over 5H, and we'll work with H's. So here we go. My cost as a function of the height of my aquarium H is given by 50 times 72 over 5H plus 50H plus 10H. Oh gosh. what are we putting in for L? We're putting in 72 over 5H. How do you do? Huh? It's good? No? Alright, so let's rewrite that so it looks a little bit prettier. That's going to be 10, so I'm getting C of H equals 720 over H plus 50 H plus 2 H plus 144. Numbers are hard. Can we get it? Yes! Can we consider a domain? Well, we can certainly consider it. If I consider permissible values of H, I see that 0 is not permissible, and so I won't be able to have that kind of left endpoint with a bracket for my closed interval method. Although I could certainly choose something that's close to 0, like 1, when I go and do my final verification in my XY chart. And we could continue increasing that height taller and taller and taller, and then just be using less and less material on my length. And so this is a situation, again, where we don't have a specified interval. We don't have the closed interval, although we will be able to choose an H value on either side of a critical value. All right, so let's go ahead and take this over to the next page and use the first derivative test as our strategy then, since we don't have a specified interval. All right, so first derivative. Oh gosh, I'm so glad we know our derivative rules, even when we have, right, these rational functions. I know the derivative of 720 over H is still just a power rule. And so the current exponent on H is -1, right? -1 times H to the -2. And so it looks like my C prime expression would be given by -720 over H squared plus 50 cent. And then the derivative of that constant 144 is just 0. Is that good? Now I'll go ahead and rewrite this again. I've got that rational term, so I'll go ahead and write this as a single fraction by multiplying this bad boy by H squared over H squared. And rewriting. So I'm getting C prime of H is given by 50H squared minus 720 over H squared. Now consider those values of H for which C prime is undefined or equals 0. So I'm going to set the top equal to 0 and set the bottom equal to 0 to determine my critical value. And as I look at my top, it looks like my top might equal 0 when 50H squared equals 720. That would happen when H squared equals 72/5, which in turn would happen when H equals the positive or negative square root of 72/5. Since H is a height, we can purposely strike the negative value of H and keep my critical value of root 72/5. I'm not going to go and try to reduce that radical at all, and just leave it like that. And we'll go ahead and perform our analysis. So we need a C prime number line. So my C prime number line labeled with my critical H value, which was root, I'm going to figure radical. Root 72/5, and to give us an idea of what that might be, right? 70/5 would be 10 plus another, so it would be like 14, and the square root of 14 would be in between 3 and 4. So it looks to me like this is in between 3 and 4, right? This is in between 3 and 4. So I'm going to go choose a convenient H value to the left of root 72/5. So I'm gonna pick 1. If I choose 1 and plug it into my green C prime, I would get 50 minus 720 over 1 is 50 minus 720 is very negative. So I get negative values for C prime if I'm looking to the left of root 72/5. We said this was in between 3 or 4, and so if I choose 5 or 6, is anything, maybe I could do 6, and then I'd be able to reduce that 720 and have a shot without a calculator, maybe, and always knowing I could go to my home screen right now. So I do 6 for H. 6 squared is 36, and 20 over 36 is 20 is 20. 50 minus 20 is positive. Totally did that without a calculator. Oh, yeah, I did. Even though it's Monday, Hanukkah, still did it without a calculator. And we're now ready to see what value is produced at a height of root 72/5. So let's go ahead and make our chart. And on our chart, what do we want? We want H, C of H. And we need to put our critical value of root 72/5 on here. What else am I going to put in here? Right, what else am I going to put in here? I don't know. I'm going to put something on either side just to verify, to confirm, right, my findings from my number line. This is not the end of the interval. I'm just picking something on either side to verify. What would be something to the right of that? That might be easy to evaluate. Well, we did 6 last time, and that worked out okay. Right, we did 6 last time. It looks like we could do anything though, because it's 720. So maybe 10 would be easy to evaluate. 10. Maybe 10 would be easy to evaluate. Let's try. Ready? When I plug in 1 into C of H, I get 720 plus 50 is 770, 870. 910, 914. So I'm getting about 914. You guys can check. When I plug in root 72/5, that's where the excitement begins. So I don't know what happens with root 72/5. So I'm giving up on that. If I enter my little store trick there, I'll get 720 over alpha A plus 50 alpha A plus 144. Looks like $523.47, about. And if I choose 10, I get 72 plus 500 is 572, 672, 712, 716, about. Why did I choose these values over here? Just to verify this is in fact was a minimum in comparison with surrounding function values, as my C prime number line indicated. How do we do? Yay! We win. So what was the original question? Was it where are the dimensions, or was it what's the minimum cost? Minimum cost? Yes! Minimum cost. So we're almost done. So minimum cost to construct an aquarium and with satisfying the given constraints. And then that was pretty sweet. It is $525.47. Math works. And it's powerful. We are going to fold off of this minimum parabola problem and get right to our second objective for the day. We're going to use the Fundamental Theorem Calculus Part 2 and apply it to graphs a third time now. We've done this a couple of different times together. And then you're going to have a chance to practice with our H of X handout. So at this time, I'd ask that everybody find your P of X handout. Don't be misled. It looks very similar to your H of X handout, but we're going to do the P of X together, then you're going to do the H of X first hand. All right. suppose that p is given by an integral defined function. The integral from -2 to x of f of t dt, where the graph of f is shown. We know from the fundamental theorem of calculus part 2, if p is given by the integral of f, then the fundamental theorem of calculus part 2 says that p prime of x is what? Well, it's my integrand function with my independent variable substituted in. So if p is the integral of f, then p prime is f. All right, let's go ahead and answer some questions that are asked then using that information. If p of yes, indeed. If p is given by the integral from a constant to x of f of t with respect to t, then p prime of x is f of x. Right, absolutely. So p prime of x is f of x, which means we're looking at a picture of p's derivative. Here's my f. So we're looking at the function p's derivative. All right, so let's go ahead and answer some questions. Can we find p of -4? Well, absolutely. P of -4 simply says evaluate the function p that accepts input values of x, except everywhere you see an x, don't put x, put -4. So this would be a straight evaluation question where I could plug in -4 into my definition for p. Graphically, I can interpret this definite integral as an area problem, where I'm scanning from my lower limit, -2, towards my upper limit, -4, and accumulating area, such that any area above the x-axis counts as a positive contribution when scanning from left to right, and any area above counts as a negative contribution. Below counts as a negative contribution when scanning from left to right. It's just that I'm scanning from x equals -2 till x equals -4. So we can handle this in two ways. We could flip it right now and put a negative sign, right? We can switch the limits, lower and upper limits. We can switch them and imply negative, or we can just interpret that as a opposite of what we normally do. So I'm going to go ahead and scan and accumulate area. Looks like an accumulate 2 units, 2 square units. That's above the x-axis, but since we were scanning from right to left, that's going to be negative. And so I'm getting -2. Did you guys get -2 for that? Okay. Keep in mind you could have flipped the limits and done opposite of -4 and -2. We'd scan from -4 to -2 and accumulate 1 and a half is 2 units. But because I flipped the limits, I need to apply the negative. In either case, I get -2. You guys good with A? B. Find the zeros of P. Well, P has zeros for sure, right? When my upper limit is -2. How come? Because as I scan from -2 to -2, how much area can be accumulated? None, right? And so I've got a 0 of the function P when x equals -2, my lower limit, for sure, right? We saw that last unit as well. And so P has zeros at x equals -2. Because I can accumulate 0 area as I scan from -2 to -2, so P equals 0 when x equals -2. Are there any other places? Well, now I'll have to consider. So as I'm scanning from -2, right? As I'm scanning to the right, I'm accumulating area, and I'm picking up 1, 2, 3, 4, 5 units as I'm scanning to the right. So I now have P of 1 is 5 because I've increased P's value by 5 units in the course of scanning from -2 up until 1. These will be canceled out by an equal and opposite amount by the time I get to 4. So it looks like based on equal and opposite contributions, this area above is canceled out by an equal and opposite area below. By the time I get to x equals what? X equals 4. So x equals 4 is a 0. If I continue scanning, it looks like this now negative contribution is canceled out by an equal and opposite positive contribution again. in the span of x values from x equals 4 up until x equals 6. So it looks like I have 3 zeros. P has zeros at x equals -2, at x equals +4, and at x equals +6. Wait a minute, we didn't scan the other direction though. If we scan the other direction, will I run into any zeros? Well, if I scan from -2 to the left, right, from right to left, then that above the x-axis will count in the opposite sense. It'll be down 1, 2 units. We already did that. P of -4 is -2, and so that's not a zero of the function because P doesn't equal 0. Awesome. So I have 3 zeros. All right. Let's find the absolute maximum of P on -4 to 6. So it looks like we've got a closed interval now from -4 to 6. Let's find the absolute maximum of P on a specified interval. This sounds familiar, but now in the context of the FTC Part 2, I know that an absolute maximum can occur in one of two places. It can occur at a critical point or at an end point. And so what I can do is simply compare the y values at my endpoints of the interval and any critical values in between, and then through inspection determine the greatest function value attained. That has to be the absolute maximum attained. So let's go ahead and say that absolute extrema, in this case absolute max, must occur at an endpoint or at a critical point. It looks like P has zero values when P prime equals F equals 0. Does that ever happen? Does P prime, which equals F, the graph I'm looking at, ever equal 0? Or is undefined? Well, it's never undefined. Right? We've got line segments everywhere. So it looks like -4 is already an endpoint. 1, 5, and that's it. We should probably say never undefined in this graph. So we have critical values at x equals what? -4, that's also an endpoint. 1 and 5. All right. So let's go ahead and I'm going to add in a page here quick. I think I want to do this. All right, so what do? We make an XY chart, and on that XY chart, we include my endpoints in the interval and any critical values in between. So here we go. Instead of an XY chart, this is going to be an XP of X chart. What are we putting on it? We're putting in critical values and endpoints. So we need -4 and we needed 6. We'll include any critical values along the way. It looks like P prime equals F has zeros at -4 is already on there, 1 and 5. Is that it? Now let's go ahead and evaluate my function P by considering it as an area accumulator. Scanning from x equals -2 to -4, P decreased in value. It would decrease by 2 units, so -2. Scanning from -2 up until 1, we add, let's do it. We add 1, 2, 3, 4, 5 units. Half times base times height triangle, 5 units, 5. So I'm getting 5. You guys get that? All right. Scanning on, I get till 5. Gosh, so I cancel out. I'm back to 0 by the time I get x equals 4, and then down 1 unit because that square unit is below the x-axis as I scan from left to right, therefore it's a negative contribution. So is that right? -1. And lastly, I will cancel that out and be back to 0. We already saw that x equals 6 is 0. So what do we do for absolute extrema? We compare the y coordinates produced by the endpoint x values and the critical point x values and select the appropriate, right, answer. It looks like we want an absolute max, so absolute max must be what? The greatest function value attained is 5. Does everybody see that? That's the greatest function value attained. So 5 must be an absolute maximum for my function p on the interval -4 to 6. Are you guys good with your area calculations with the squares and triangles and rectangles? We do that okay? Awesome. Great. Can we put it all together and make a sketch? I believe that we can. So we're going to go ahead and take a look at my p prime equals f graph, and we're going to take those points that we just calculated, and we'll be able to make an accurate sketch. And so what do we need? We need my endpoint values. -4 was -2, so -4 comma -2. We had zeros as -2, 4, and 6. We can add those. -2, 4, and 6. Now we can go ahead and include additional points that we calculated. P has an absolute maximum at x equals 1 when the value of P is 5. So we need 1, 5. And we need 5, -1. All right, let's see if we can't put it together now using our knowledge of function behavior and the relationship between original function P and its derivative P prime equals F. So if P prime equals F is a constant increasing line segment on the interval -4 to -2, then P must be not degree 1 linear, but degree 2 parabola and right side up. So can I draw a parabola right side up on -4 to 2? Yes. If P prime equals F is constant linear on the interval -2 to 0, then we should be constant increasing on the interval -2 to 0. And we're going up by how much? Well, it looks like we're going up 1, 2 units, 3, 4 units. Line segment. At x equals 4, looks like we have a decreasing linear prime. Means we have upside down parabola. So up 1 unit, down 1 unit. And then down 2 units. Down 2 units. Oh, hey, we ran into there. That's good news. And then positive parabola and line segment. Put it all together. What do we have? We've got our picture of P, whose derivative P prime equals F was shown. How do we do? So I'm going to have a hard time exporting this, just want you to know. So I'm going to clean that up just a little bit. You guys are fun. All right, let's finish it out with our closure for the day, where we've got some nice graphical relationships. I'm going to go ahead and call on you to share your responses, so please write something in each of the blanks, and I'll pause the recording to give you a chance to do that. Okay, ladies and gentlemen, go ahead and share your response with the whole class when I call on you. So this was trying to get you, right, climbing on different rungs of our proverbial derivative ladder when y is concave down when y prime is doing what? So y is concave down when y prime is doing what? Marissa? Decreasing. Good. We know that we know that y is concave down when y double prime is negative. If y double prime is negative, that must indicate decreasing behavior in y prime. Raise your hand if you had the same as Marissa. When y prime is decreasing. Next time, you guys. If f prime of c equals 0 and f double prime is negative, then f must have a blank at x equals blank. Grace?
Oh, relative maximum at x equals 3.
Must have a relative max at x equals c. Raise your hand if you have relative max or local max. Good. This indicates horizontal tangent but concave down behavior must indicate the top of a hill, the top of a peak. And so that would be a relative maximum. Nice job. If h prime equals 0 and h double prime is positive, so now we're concave up behavior is horizontal tangent, then the point c comma blank must be a blank. What? The point c comma blank must be a blank. Evie?
C comma 0 must be a local minimum.
So if I'm going back to my original graph, right, that horizontal tangent and concave up behavior could be anywhere in the xy coordinate plane. So how would I get that y coordinate to determine the local minimum value? H of c, right? That would be the value of my function h at that x equals c value, the particular point of concern. Good. Who had c comma h of c must be local min. C comma h of c must be local min. And lastly, my fundamental theorem of calculus part 2, if k is given by the integral from constant a to x of f of n dn, then what must be true? James?
That equals success.
What does?
Integral part.
The what equals?
K of x.
Yes, k. I saw it on your paper. K
prime.
K prime of x. The derivative of k prime, is given by f of x. Absolutely, good job. That's my fundamental theorem of calculus part 2. Strong work, you guys. I'll go ahead and save these notes and then post our recording tomorrow. Great job today. Don't forget about our schedule after spring break. They'll be coming back right during your Unit 8 test, so let's make it a good one.